So last time we talked about directional derivatives, and we said, you know, there's this wonderful thing called the gradient. Now, if you recall the gradient, it is the vector which consists of all your partial derivatives. And so if you have a function of two variables, x and y, the gradient vector says, okay, what's happening with respect to x, partial f, partial x, comma, partial f, partial y. So it is a vector, and we said, okay, what can we do with it? Now, sort of the big thing, there were two takeaway messages from last time. We're going to go even further this time, to say, well, the gradient in many ways acts like we expect a derivative to behave. In other words, it has the properties of derivatives in terms of various rules, and it also mimics in the sense that it's kind of acting almost like a slope for the tangent plane, where it's telling you how the tangent plane tilts in each direction. The other thing, of course, is that the gradient can be used for directional derivatives, as already mentioned. So we want to build off of that and establish a couple of really cool ideas, things that you can do with the directional derivatives and the gradient. So recall that this stands for the directional derivative of the function f at the point P in the direction u. So u is a unit vector. And the way that you compute this is you say take the gradient of your function at P and dot it with u. Now, the dot product has a nice property. So that's the other thing to recall. V dot u, the way you can find this, and when we say find this, we mean geometrically find this, is you take the magnitude of v times the magnitude of u times the cosine of the angle between the two vectors. So we say, okay, well, let's combine these. So if I take the directional derivative of my function f at my point P, it's going to become, by combining these two rules, the magnitude of the gradient times cosine theta, where theta is the angle between where the gradient points and u. Now, cosine theta is a function we understand to a fair amount, and it's always between -1 and +1. So because of that, we can say, well, this term, cosine theta is between -1 and +1, means that the directional derivative is always between negative, the magnitude of the gradient, and positive, the magnitude of the gradient. So from this, we can now establish a couple of properties about the gradient. So here we go. The gradient has a direction because it's a vector. The direction of the gradient is the direction of greatest increase. Because if we want to make this expression as large as possible, in other words, to achieve the magnitude of the gradient, we would choose cosine theta to be 1. That happens when theta equals 0. So the direction of the gradient is the direction of greatest increase. The magnitude of the gradient is the size of the greatest increase. So the moral is, if I want to know about, I'm at a point, and I want to say, I want to move in the direction of greatest increase, the answer is follow the gradient. Well, what if I want to go down? Well, that's not so bad. If I want to go down, in other words, I wanted to have the greatest decrease. Well, the greatest decrease is this other side, negative the size of the magnitude of the gradient. And the answer is, choose your theta so that cosine theta is -1, which means theta equals pi. That means you're going exactly opposite. So negative the gradient points in the direction of greatest decrease. So again, the negative of the gradient tells us how to go down as fast as possible. And negative the magnitude of the gradient is the rate of greatest decrease. All right, so we have those basic facts. All right, let's do a quick example. Find the unit vector pointing in the direction of the greatest decrease and amount of greatest decrease at the point, which is currently blank, for the function f of xy equals, which is also currently blank, which means it's a choose your own adventure type problem. All right, well, let's put our function first, then we can decide what our point should be. What do you want the function to be?
X to the x.
You really want x to the x? Since no one else is saying anything. X to the x.
Plus 100.
Plus 100. Okay then. Now, we'll talk about the plus 100 in a moment. We maybe should have something with y involved.
Times secant squared xy.
Times secant squared of xy. Okay. Well, great. So we're going to choose our point at x equals 1 and y equals 0. Why not? Those are the numbers I like. 1 and 0. Two most popular numbers for mathematicians. Okay. So here's our function, f of xy. And I'm glad to see that this is a class that does not shy away from a challenge. So, good. Good. All right. So, if I want to find the unit vector pointing in the direction of the greatest decrease, what should I start by finding? Well, magnitude, we can't do anything with magnitude because there's no vector yet. The gradient. Gradient. We need a vector. We know we need a vector because it says vector. The fact that we're looking for vector of greatest increase or greatest decrease says we're looking for the gradient vector. All right. So, the gradient of f is the derivative of x to the x with respect to x is sorry, what? It does start as x to the x. That is correct. Anything else? Plus what?
ln of x.
Okay. Sure. Anything else? Well, there's also a plus x to the x, so we shouldn't forget that. And don't forget there's an x there. Derivative of 100 secant squared of xy will be 200y secant squared of xy tangent of xy. Comma. That's our first entry. What's our second entry? Well, derivative with respect to y. Derivative of x to the x with respect to y? Oh, that's nice. We should have that at the start. Derivative of 100 secant squared of xy with respect to y? 200x secant squared of xy tangent of xy. Now, are there any questions about these derivatives? Anything you're like, I'm not 100% sure I believe that one?
Where did the plus x to the x?
Where did the x to the x come from? Well, good question. So how do you take the derivative of x to the x? And there's sort of, I should use a color that's going to show up. If I have x to the x, there's sort of two schools of thought. Should I think of it as the variable is in the downstairs? So suppose for a second I said, this is the part that's varying, and that part I'm going to leave alone. So it's like x to a power. If it's x to a power, what do? Well, you bring the power down. So it'd be x times x to 1 less power. But of course, x to 1 less power times x is x to the x. Now that's if I were to think that this were the part that we're varying. On the other hand, I could say, no. That's the wrong thing to do. You should think of this as the fixed part, and this is the varying part. So it's like a constant to the x. in which case the derivative of a constant to the x is the constant to the x times the log of the constant. So the question is, which one is right? And the answer is both. And you combine the two together. So you get x to the x plus x to the x log x. Now you're probably thinking, I don't think that's how calculus works. Okay, you're right, that's not how calculus works. The real way to do this is x to the x can be written as e to the log of x to the x. Because e to the log x is still x, which means that you can write this as e to the log x times x. And now once you do that, you say, okay, well, the derivative of x to the x is that derivative of e to the log x times x. So that's e to the log x times x times, doing the chain rule, derivative of log x times x. Okay, whoops, I forgot an x there. All right. Derivative of log x, 1 over x, times dx, plus log x times 1. Well, this is x to the x times 1 plus log x. And so if you multiply through, you'll see that's what we have. All right. I thought people might challenge that 200y secant squared xy tangent xy, but cool. Now, are we done? No, not yet. What's next?
Magnitude?
Now we need to, well, before we do magnitude, we should evaluate. Because I wanted the gradient at a very particular point. I'm asking at a particular point what's happening. And now that I'm at the point where it's like, okay, I've taken my derivatives, I'm going to evaluate. 1, 0. 1 to the 1 times log of 1? 0. 1 to the 1? 1. 200 times 0 times secant squared of 0 times tangent of 0. 0. Okay, come down here. 200 times 1 times secant squared of 0 times tangent of 0. 0. Okay, so it turns out this is not a very interesting problem for the rest of the duration of the problem, but that's okay. We'll make sure to put interesting problems on future exams. But now, the next question is this the right vector? Now, unfortunately, the answer this time is yes. Most of the time, the answer is no. Let's pretend like the answer wasn't yes. Why would it not be the right vector most of the time? Because most of the time, it's not a unit vector. Is this a unit vector? Yes, it is. So that's why it's like, oh, not so exciting. But, so this is the unit vector pointing in the right direction. Now, normally, the gradient is not a unit vector. So what do? Divide by its magnitude. Ah, okay. But we also need to find the magnitude because amount of greatest decrease. Oh, wait, this is not our right answer. Ah, why did I box it? Oh, look, it's a squiggly line, which means it's an intermediate step. There we go. All right. This is the direction of greatest increase. We want the direction of greatest decrease. So what do? Yeah, multiply by negative. So direction, in general, it would be minus the gradient at 1, 0 divided by the magnitude of the gradient at 1, 0. And this assumes that I wanted a unit vector. So it becomes the vector negative 1, comma 0. The amount of greatest decrease, well, it's minus the magnitude of the gradient. So in this case, what do you get? Negative 1. All right. There we go. Okay. Phew. We survived that one, I think. Now, there is one more great property of the gradient. In some sense, you can kind of guess where we're going to go next. We said, okay, theta equals 0, theta equals pi. That leaves one more interesting angle to talk about. So we're going to get to that angle. But before we do that, let's recall something about level curves. So what's a level curve? So a level curve is just a way of saying, I want to take my function, and I'm thinking of my function now as a surface. I have this z equals f of xy. So here's my surface. And what I'm going to do is I'm going to take my surface z equals f of xy, and I'm going to take a slice. Now, not just any slice. I'm going to fix a slice at a particular height, or if you will, a particular level. So when I slice my function here, I'm going to hit on pieces of it. And in particular, what will happen is that I'll tend to hit along the curve. So what you see here is that if you take this z equals k slice and you pull it out and lay it down, looking at it from above, so in other words, what you see here is you see what would be, looks like the xy plane, but of course it's really an xy plane where I have z at a particular elevation. So the intersection that I see on the curve translates into this part of my level curve. So that's the level curve. Now, what's the important thing about level curves? Well, if you look at a level curve, the function z equals f of xy is constant along a level curve. It's a definition, because the function is constant just means that the outputs are the same. And now the next part, I might as well show it now. There's this claim. It says, suppose now I want to take a directional derivative, but I'm not just taking it in any direction. I want to follow the level curve. That is to say, I'm at a point here. Here's my point, and I choose my direction u to be following that level curve. So u is tangent to a level curve in the plane, in my inputs. What's going to happen? The claim is we're going to get 0. Well, why is that? Well, you should do what we almost always do, which is pull out your magnifying glass. So if you pull out your magnifying glass, what you'll see here is that we have this curve. And when I'm talking about the directional derivative, I'm at this point and I'm moving just ever so slightly. And I'm just barely nudging myself along that level curve. I'm not changing much. I'm moving in the direction of the level curve, but I'm barely changing my position at all. But because I'm moving along the level curve, I'm going to stay on the level curve. At least very small local change, I'm essentially going to stay on that curve. And on that curve, I'm constant. So there's no change. That's the idea. As I move in the direction that the curve is telling me, I'm not going to be changing my elevation. If I don't change my elevation, that means my output doesn't change. When we're talking about the directional derivative, we're asking what's happening to the change in your output. And the answer is it's not changing. So it's 0. Okay. Well, what does that tell us? Well, it tells us the last thing we need to know about the gradient. The gradient is perpendicular to level curves. So we can now sort of identify what's happening. So if I'm at a particular point, as I am here in this sort of blow up, what I'll see is that if I want to go up, I'm going to be perpendicular to the gradient. And when I say go up, I want to say go up as fast as possible. If I want to go down, I'm also going to be perpendicular to the gradient. And if I just want to chill and hang out, I say parallel to the level curve. So I said perpendicular to the gradient. I should have said perpendicular to the level curve. Up, down, stay the same. Okay, so that's our basic philosophy. Now, we're not going to use this too much for functions of two variables, but here's the thing. The same idea and process works for any number of variables at all. And so we can do the following. Instead of thinking about level curves, we can start thinking about level surfaces. Now, what's a level surface? Well, that's when I have a function of 3 variables. So W is g of x and y and z. And that's really hard to figure out what's going on because we can't really plot it. But we can say, okay, what I can look at is I can look at a slice where I hold the output W to be fixed. So g of x, y, z equals something. And, whoops, typo here. That should be the letter G. Fix that later. So what's going on is to say, if I want to be perpendicular to my level surface, what should I do? I should say, what's the gradient? So the gradient will be perpendicular to my level surface. And of course, another word for perpendicular, whenever you hear the word perpendicular, you should think normal. Normal. Okay. So this is sort of like this could be useful. Because there are things that we want to find, which we want to find normal vectors for. In particular, let's talk about planes. So tangent planes. We now have 2 methods. We just saw the second method hinted at. We're going to make it explicit here. So if I want to make a tangent plane, the first method is what we talked about previously. Well, it says, let's look at our partial derivatives. So then z would be f of ab, and you can think of it as the f of ab is telling you how far up and down vertically to shift. The partial f partial x tells you how much to tilt in one direction. Partial f partial y tells you how much to tilt in the other direction. And that gives you your plane. So z is f of ab plus the derivative with respect to x at ab times x minus a, plus the derivative with respect to y at ab times y minus b. Now there's a second method, and the second method is used in a slightly different setting. So the first method is, suppose I have z is written as a function of x and y. Second method says, suppose you don't have that. Maybe you can't even get it. But you have an expression of the form f of a function of x, y, and z equals k, where k is a number. And now, the key here is to say, wait a second, this part here, this f of x, y, z, comma, k, that's not just anything. This is a level surface. And so I say, I know how to find something which is perpendicular to a level surface, namely the gradient. So that tells me how to find a normal. So now I can say, well, if I have a point, ABC, the gradient at ABC is the normal vector. So then if I take the normal vector dotted with x minus a, y minus b, z minus c, I get 0. This is just a way of saying a normal vector and the point a, b, and c. And then you write it down, that's the equation for the plane. So now, let me just make a side note. We're going to go through it really quickly, which is to say, these two methods are compatible. In other words, if there's a setting where you can use both, you will get the same answer. Now, which one should you learn? The answer is, learn both. It really is a matter of what format are you in. Are you in the setting where you have z as a function of x and y? If you are, use that first method. That's geared for that situation. If you're in a setting where I can't solve for my variables, sort of like an implicit, if you will, but I can say f of x, y, z is k, use the second setting. Now, to say that they're compatible says what? Well, suppose for a second I'm in the setting z is f of x, y. What I can do is I can create a new function called capital F, which is little f of x, y minus z. And then I say, well, I just want to know, when does this equal 0? So, what do I need? Well, what's my point? X equals a, y equals b, and z is f of ab. What's my gradient? Well, partial f partial x, partial f partial y, -1. So you take your gradient dot x minus a, y minus b, z minus what z should be, f of a, b. You rewrite it, rearrange it, lo and behold, this pops out. So you get the same answer. But you should get the same answer because they're finding the same thing. Let's do an example. I like examples. Any questions? I hope that the example will help shed insight. Find the tangent plane at the point 0, 1, 2 to the surface x squared plus e to the xz plus yz is equal to 2 plus cosine of x times y. So this is a surface. There is some surface out there which consists of all the points which satisfies this relationship. Now, among all the points which satisfy this relationship, there's a claim that 0, 1, 2 is one of those points. And to verify, what you would do is you would plug in x equals 0, y equals 1, and z equals 2. And if you do that, you'd get 0 plus e to 0, which is 1, plus 2, which gives you 3, is equal to 2, plus cosine of 0, which is, again, 3. So 0, 1, 2 is a point which satisfies this. There are many more. So it makes some sort of strange-looking surface. But try as you might, you will never be able to solve for z, because it's in two places. And if you free a z from here, you're going to trap this z inside of a log. So you're kind of stuck. You cannot explicitly solve for z. So method 1, where we have z as a function of x and y, is off. We can't use it. So what should we use? Maybe method 2. It's an idea. It's an idea. So we have it here for convenient reference. So what we'd like to say is, can we write it in the form the function equals a constant? Well, is it in the right form? No. Okay, so does that mean that there's no hope for finding this tangent plane? No, there's no hope? Or no, there is a hope. A new hope, if you will. Well, what do we need? Well, we need to get a function equals k. We're almost there. We just have to move that across. And if we did that, we'd get x squared plus e to the xz plus yz minus cosine of xy equals 2. So rewrite it so that it's in the form function of x, y, z equals a constant. It doesn't matter what the constant is. It just needs to equal a constant. So it's okay to leave the 2 on the other side. We don't have to move the 2 across. Whether you move it across or don't, it won't make any difference to the rest of the work involved. All right. So now we're in the right setting. F of x, y, z. I can really think of f of x, y, z. This is, again, a 4-dimensional object. But what I'm doing is I'm saying f of x, y, z equals 2, which is like taking a slice. When I take a slice of a 4-dimensional object, I get a 3-dimensional thing, which is that surface in 3 dimensions. All right, well, what happens? The key is to say that the gradient is going to be the normal vector, and that's pretty much it. You know, once you remember that, the gradient is the normal vector, everything else works pretty quickly. So, because this one was not done by asking for suggestions, I suspect the gradient might be reasonable. What is the gradient? How do we start? 2x, then z to the xc. The yz what happens there? 0. And then? It will eventually become a plus. Initially, the derivative of cosine is negative sine. Minus minus makes plus. Sine xy, anything else? Times y. Okay. Comma. Now what? Z. Anything else?
Z plus x sine.
Okay, x sine of xy, comma, and I need to wrap around. Now taking it with respect to z, x e to the x z plus y. Anything else? Nope, good. There's the gradient. Now, pause for a moment. Is the gradient my normal vector? Not yet. See, you have to remember there's a subtlety. So like the derivative, we say, well, the derivative is a slope, but it's not quite that the derivative is a slope. The derivative is a function. How do you get a slope from a derivative? You evaluate it. How do you get a slope from a gradient? Yeah, you evaluate it. So when you have variables, that's not a normal vector yet. You need numbers. And so you get those by evaluating. So now, where do we evaluate? 0, 1, 2. So, gradient of f evaluated at 0, 1, 2. Well, 2 times 0. 0, that's good. Then I have z, which is 2, times e to the 0. So that'll be 2, because 2 times e to 0 is 1. Then I'm going to have sine of 0 times 1 to be 0. So the first entry is 2. Go to the second entry. Z will be 2. 0 times sine of 0 is extra 0y, 2. All right, next entry, we're going to have x, which is 0, e to the 0. So the first term will be 0 plus y. Well, at y equals 1, that becomes plus 1. So 2, 2, 1. So that's the normal vector. Of course, when we say the normal vector, we really always mean a normal vector, because there's many possible normal vectors. We just need one. The gradient gives it to us. So the 2, 2, 1, those are the coefficients. 2x, 2y, and 1z. So the last part to finish off the plane is to say what goes over here. Well, how do you figure out what comes down the other side? Plug in the point. 2 times 0, 0. 2 times 1, 2. 2 is 2. Put them together, we get 4. And so there's our tangent plane. This is a very popular problem. Well, maybe I'll say it's a popular problem among faculty. I don't know if it's popular among students. All right, another choose your own adventure. Find the tangent plane to, and then there's nothing else. Which means that we could do a tangent plane using something of two different forms. We could have our expression be z as a function of x and y, if you want to practice with that, or we could have a function of x, y, z equals k. Is there a preference? Should we be in method 1, z is fxy, or method 2, f of x, y, z equals k? You're going to do a 1? Ooh, interesting. Okay, we need practice, I see. Okay, so we want to have z equals. So I need now a function of x and y. What would you like? And let's avoid power functions to functions. We've already practiced that today.
Arctangent of x to y squared.
Arctangent of x times y squared?
Yeah.
Okay. Anything else?
to the 20, y to the 19.
Well, we'll see how well this ages. Okay, x to the 20, y to the 19. All right, and we need a point, and we will pick at, should we do 1, 1? Yeah, we should do 1, 1. If we do 0, 0, there's going to be so many zeros, nothing will be left. Okay, so at 1, 1. So, right now, this is our f of x, y. So our formula for reference, let's just remember, is it's f of ab plus f sub x at ab times x minus a plus f sub y at ab times y minus b. Now at the end, we'll essentially do the same amount of work that we do to take a gradient, because the gradient would be the partial derivatives. You can even take the gradient, just remember, oh, it's just the partial derivatives. But for us, we'll work through what we get. F sub x. So f sub x, what is that? Well, the derivative of arctangent of xy squared with respect to x.
Y squared over 1 plus xy squared squared.
Okay, y squared over 1 plus xy squared squared. So the derivative of arctangent is 1 over 1 plus whatever's on the inside times the derivative of the inside. And we're taking the derivative with respect to x. How about the derivative of x to the 20th, y to the 19th? 20x to the 19th, y to the 19th. All right, good, that's done. F sub y, well, what will that be? Well, it's going to look suspiciously familiar. Again, arctangent, 1 over 1 plus the inside squared times the derivative of the inside, derivative of xy squared with respect to y, 2xy. Derivative of x to the 20th, y to the 19th, 19x to the 20th, y to the 18th. Any questions? All right, so we've taken our function, we took our partial derivatives. What comes next? Plug in. And plug in where? 1, 1. So f sub x at 1, 1. Well, that's 1 over 1 plus 1. See, that's the nice thing about 1. It's very easy to evaluate. 1 over 1 plus 1 is a half. Then I have 20 times 1 times 1. Because 1 to any number is 1. So you get a half plus 20, which we can write that as 41 halves. 20 and a half. F sub y at 1, 1. What will that be? Well, it'll be 2 over 1 plus 1, so it'll be 1 plus 19, so it'll be 20. Or if you like, it's 40 halves. So now we can say that z is equal to, oh, there's one other thing we have to find. What's the function at 1, 1? When we plug in 1, 1, we get arctangent of 1, which is pi over 4. And then we get 1 to the 20th times 1 to the 19th, which is 1. So there's my function at my point, plus f sub x evaluated at my point, so 41 halves, times x minus what? 1. Because this first one is my a, and this second one is the b. Then plus 20, which is f sub y 1, sorry, f sub y evaluated at 1, 1, times y minus 1, which is the y minus b. And there we go. All right. Cool. So now we can do both. Well, what can we do with these things that we are finding? We like tangent planes because they give us a way to approximate the function. Oh, there's a question, yes.
Could we also do that using the gradient if we move the z over?
You could absolutely do this if you using the gradient if you move the z to the other side, because they will give you the same answers. It's not any more or less work. It's basically you go through the same processes. You're still going to find the partial derivatives. You'll still get the same answer. All right. So one of the nice things is that tangent planes give us a way to sort of get a local estimate of what the function is doing. Because the idea is that tangent planes are approximating the behavior of the function. So if I want to understand what the function is doing, and it's hard to understand the function, I say, well, okay, second best thing is what is the tangent plane doing? That gives us a pretty good guess. Now, I'll say it gives us a pretty good guess. It's really contingent upon one thing: how much we believe in this approximation. Well, how much we believe in the approximation basically depends on how close you are. So if you are very close to your point of tangency, generally we call that the point AB, the approximation is usually reasonable. As you move further away, it basically becomes less reasonable to the point of it's silly to even consider the tangent plane once you're very far away. Now, of course, I'm not defining what very far means because it is dependent on the function. So if you take a look at what you have, it says that the change in the output, which we represent as a delta, as representing change in, so the change in the output, delta z, is approximately what happens when you look at how is your x changing, or the rate of change with respect to x, times the amount of change in the x direction. So this f sub x at AB, that's the rate of change of the function f with respect to x. Delta x is how much x changes. Therefore, you can say, well, what's happening here is this is how much is changing the output based on how far you move in the x direction. Similarly, you have FYAB, the rate of change in the y direction. Delta y is the amount of change in y. So you say, okay, I'm changing at this rate in the y direction. I've changed my y input by this amount. Therefore, I'm going to have a change in my function. Now, you might say, well, okay, that's only taking change in x and change in y into account. Is that reasonable? And the answer is if you're differentiable, it turns out it's okay. We will get better next time. And we'll get really good next time. Well, we'll get decent. It takes some work. Now, there's a side note here. There's something called differential notation, which you don't really need to worry about. But if somebody ever says differential notation, the idea is instead of saying the actual change in the output, which is delta z, we're going to call it dz. And we're not going to get an approximation. We're going to be exact. But what's happening is we're no longer looking at what the function does. We're saying what happens on the tangent plane. So the tangent plane is an approximation. All right, so really remember this first formula. And you might say, haven't we seen this first formula 2 or 3 times already? Yes, you have. You see, it's such a great formula. It deserves multiple lectures because of all the wonderful things we can do with it. All right, so now sort of the punchline where it says down at the very bottom, remember that the tangent plane, it's acting like the function nearby. So when we're trying to get approximation, use the tangent plane to approximate. All right, so we have time for a few examples. So suppose you're given that f of xy is 2x cubed plus xy minus y cubed, and you want to approximate f of 2.03 comma 0.98. Now you might say, that seems unusually precise to approximate. And to add, for some reason we want a very interesting set of numbers approximated when we don't have a calculator. We're again stuck in our desert island. We have our coconut technology, so we don't have our calculators with us anymore. But we want to approximate this. All right, what do we do? Well, we look at these numbers, 2.03, 0.98. What are they close to? 2 and 1. So I say, you know, here's a really bad approximation, f of 2 and 1. Well, it's not terrible, but okay, first level. And so we plug those in. So for instance, 2 times 2 cubed, well, 2 cubed is 8, times 2 would be 16, plus 2 times 1 would be another 2 added onto that, and then 1 cubed is 1. 16 plus 2 minus 1 would be 17. I should say that is f of 2, 1. So I could say it's about 17, but we can do better. So how can we do better? Well, using the tangent plane. Okay, so what we can say is that you can say, look, f of xy is about f of 2, 1 plus f sub x at 2, 1 times x minus 2 plus f sub y at 2, 1 times y minus 1. And we've just found that f of 2, 1 here is 17. Let's try to find some more things. This f sub x at 2, 1 and f sub y at 2, 1. So what is f sub x? 6x squared plus y. F sub y will be x and minus 3y squared. So f sub x at 2, 1 will be, well, 6 times 4 plus 1, 25. F sub y at 2, 1, well, that's going to be 2 minus 3. So negative 1. All right, so we have that this is 25 and this is negative 1. So now what I can say is plugging these values in, and I can now say f of 2.03, 0.98 is approximately 17 plus 25 times 2.03 minus 2. 0.03 plus negative 1, that's the f sub y at 2, 1, times 0.98 subtract 1. Well, that'll be minus 0.02. Because it's 0.98 subtract 1, you're going to get negative 0.02. So 17 plus 0.75 minus minus makes a plus 0.02, tells us an even better approximation than 17 is 17.77. Now what's the real answer? Well, if only we had such a way to find such a thing. It's 17.779 ... Actually, not that many dots. It's a finite number of dots. And looking at our time, we'll stop here and pick up again next time.